Thank you very much, and thank you very much for coming. Yes, my name is Adam Warski. I come from Poland. I work at SoftwareMill, and I would like to talk a bit about how to design a programmer-friendly API, because, well, I guess the role of an API is twofold. First of all, it has to solve some specific problem, but secondly, it has to be nice in the usage by its main user, which is the programmer, right? So when you design an API, you don't only want it to solve a problem, you also want it to be friendly to the programmer who is using it. And Scala is a very flexible language, so we have many possibilities in how we can design the API. Sometimes we have too many possibilities even. So I would like to show you how I approached this problem, but not in a general setting, but on a very focused case study, looking at a library that we've been writing for the past year, which is tapir. So that's the main topic of the talk. We'll be doing a bit of live coding, but mainly talking this time. So first we will look at what tapir does, what kind of problem does it try to solve. Then we will look at the general technique that tapir is using, which is separating description and interpretation. And it's not like tapir is not unique in using this technique. It's quite general applicable, not only in the Scala language. We will talk a bit about goals, what were the main goals when the API was designed. And finally, if we have some time left, we will take a look at some design choices, at some trade-offs that we had to make when the API was designed, because of course there are always problems that you have to solve. Before we dive in, just a short comment on who I actually am. So as I said, I'm a software engineer and the co-founder of SoftwareMill. We are a company doing custom software for a very diverse set of clients, mainly doing backends in Scala, but not only. Big data, fast data, blockchain, messaging, you know, all the fancy stuff. Yeah, and of course using fancy technologies such as Scala, Kafka, and Cassandra, though these are getting pretty old, we'll have to find some new ones, I guess. And yeah, I'm doing some open source projects like STTP client, Tapir, Macquarie, Quicklens. I did Enverse, which is a Hibernate module in my previous life. Yeah, okay. So before we talk about APIs, let's first take a look at tapir and what kind of problem does it try to solve, right? So we write HTTP APIs quite often. They are not quite dead yet. Maybe GraphQL will actually replace them in some future. I don't think they will be totally replaced, but they are still quite a common task in our everyday lives, right? And in Scala we have a couple of libraries which define APIs, which make writing the HTTP APIs quite nice. We have HTTP4S, which we have an example here. We have Akka HTTP, we have Play, and a couple of others. And the APIs they define for defining the HTTP endpoints, they are quite nice, right? You can learn them, you can become fond of them. However, there's one major problem, right? The only thing they allow you to do is define they describe the shape of the server, right? The moment you have to, for example, make a client call to the same API, you have to write another piece of code, right? If you want to document your API using, for example, OpenAPI or Swagger, which is quite standard, well, you have to do the most painful thing, which is writing YAML, which is over here, right? So all these three snippets of code over here, they all describe the same API, which is a hello world endpoint, right? So if we want to write a server, a client, and docs, we have to write three pieces of code, but we don't like repeating ourselves. So that's the problem we would like to solve, right? We don't want to repeat ourselves. So we would like to describe an endpoint using generic code, from which we can then derive a server, a client, or documentation. And we can do it using two approaches. One is to write the YAML and then generate code from that YAML, right, using a code generator. There's a lot of code generators from OpenAPI to a number of languages. Or we can describe the endpoint in the proper language, not YAML, and generate YAML from that. Okay? So I guess you can see which one I picked. So yeah, both of them have pro and cons, right? The YAML first approach has the good side that you can generate code in many languages. Like you can do Java, Go, C, whatever. However, well, the main downside is that you have to write YAML, and I don't think YAML is a language that's designed for human beings to write. It's designed for computers to read, but we shouldn't be writing any YAML. Still, people do it. I know, I think it's painful. And there are projects which work like that. That's, for example, Guardrail, right? Or the other way around is to use a real programming language, such as Scala, for example. So then we get a lot of more flexibility. We get abstraction possibilities. We get expressiveness. And there's a number of projects which take this approach as well. There's endpoints, typed API, row, typed schema, and tapir, which we will cover today. Okay, so just to show you very quickly how tapir works, I will describe a very simple endpoint using tapir's API. So the endpoint we will describe is a get. So the endpoint should get a list of books, and they are optionally filtered by the year in which the book was published, and the number of results is limited, right? So we will describe the endpoint more or less in plain English. So we say that it is an endpoint, and it's a get endpoint, and it has to be available under the books path, and it will have an optional query parameter, which will be a number, and the query parameter number will be year, and another one which will be limit. Okay. Now, each endpoint usually can have two types of results, right? Everything can go successfully, or there might be an error. And when dealing with HTTP, very commonly you have errors, right? However, the response you get on an error is typically quite different from the response you get in case of success. And tapir supports that like first class. So the specification, the description of the outputs in the error case is different from the description of the outputs in the success case. So on an error, if anything goes wrong, the parameters are malformed, the limit is negative or whatever, we will return a string body just describing what was the problem. And in case of success, we'll return a JSON body, which will be a list of books. A list of books, okay? And that's it. That's our endpoint description. It reads more or less natural, I think. You can kind of guess what it does. We can generate the type annotation even automatically. That's not always the case when dealing with Scala. And from the type signature, you also kind of can understand what's going on, of course, if you know what the type parameters are for. So the first type parameter specifies the values that are mapped from the input, from the request. The second type parameter specifies the type that will be mapped to the response in case of an error, and in case of success, that's the third parameter. And don't worry about the fourth, that's for streaming. And in a very similar way, we can describe other endpoints. For example, here we have an endpoint to get a single book, right? So we get very similar code. So we have a get endpoint, which responds to the book's context path, has a single path parameter, not a query parameter, but a path parameter, right? And in case of errors, we return the same. We return the same thing. Okay, so that's just like very basic tapir, how it looks from like the programmer perspective. Which one was S15? So yeah, so now we will take a look a bit on the inside how it actually works, right? So what we really want to do, like from a very high level perspective, is that we want to describe a function, right? Well, a function has an input, has an output, right? So, well, we might be tempted to describe any function, but it would probably be way too general, right? So we are restricting ourselves to the HTTP domain. So what we want to do is we want to describe a function which takes a request and returns some response, maybe producing some side effects which are described by f, right? And that definition over here of the function taking a request and returning a response is more or less the definition of the HTTP4S route, right? So over here we have the HTTPS route, and that is almost an alias for that over here with some additional decorations, right? So what is the main problem with having a function from a request to a response, right? Why cannot we just take the HTTP4S route and generate documentation from that? Well, the main problem here is that such a function is opaque. We cannot look inside. We cannot see what kind of information is extracted from the request, right? It is just some code, and we have no way of looking inside that code and seeing what do we read from the request, and what do we write to the response, right? So we cannot inspect that function. It's opaque. So we need some way of describing it, and we need some way of reifying it as code to be able to actually inspect it at runtime. And Java faced the same problem, and they solved it, of course, with annotations. So if you are familiar with Spring or Java EE, you probably have seen code like that. So here we represent all the metadata as annotations, and well, it works to some degree. It has its downsides, like the whole annotation system in Java has its downsides. The annotations in Java form like a sub-language, right? They have their own syntactic rules. They have very poor type safety. They are not composable, so you cannot abstract over annotations easily. You cannot extract common sets of annotations and so on. Well, unless there's some framework support. But it is quite clumsy, right? It's like a very poor language that's glued onto Java. So I think Scala in that regard can actually provide us with something better. And that something better is data, right? Scala is really good at manipulating data. We have case classes, using which we can represent immutable data. And that's what we do here. A description of an endpoint is just a case class. It's an immutable data structure which describes the structure of our endpoint. The input, so the description of what we read, of what we map to from the request, is just a data structure, right? We have an endpoint input, which is a query parameter, which is a header, which is a path parameter, and so on, right? And on top of these immutable data structures, we have an API using which we can create instances of these classes, right? So at the core of Tapir and a couple of other libraries, we have immutable data structures and an API which allows us to create instances of these data structures in a nice programmer-friendly way, right? So the main role of the library is to define the API to create those instances and to manipulate them, right? So for example, here when we were calling the .in method, we were really modifying the immutable description of the endpoint and adding and appending a new description of an input parameter. Okay. So once we have the data, what can we do with it, right? Well, once we have the data, we can interpret it. We can traverse the data in a couple of ways. So for example, we can write a server interpreter, we can write a client interpreter, or a documentation interpreter. And let's take a look how it works, okay? So here we have our endpoints as we have seen them before. So nothing's changed. But now we will try to write a server which actually does something with those endpoints, okay? So what we will do is we'll import an interpreter. So we will import Tapir server HTTP4S. So we will interpret our endpoint description as an HTTP4S server. Sorry, I forgot HTTP. Okay. Why is it red? Okay, so that's an old computer, it's quite slow. So what this import does, it adds an extension method to our endpoint class. So we can take our endpoint, we can take our getBooks endpoint. So if we navigate to that, you can see that that's the description of our endpoint to getBooks, and we can call the toRoute method, which is the extension toRoutes method, which is the extension method added by our interpreter, right? So this interpreter has a dependency on HTTP4S, of course, because it generates HTTP4S routes. So what we need to provide here, like the missing piece, we have the description of an endpoint, but we still need to provide the server logic, right? We need to tell the we need to specify what should actually happen when that endpoint is invoked. That's the missing piece to create a server. And so here we have two parameters, the year and the limit. So what we do is we take our year, if the year is specified, we filter our books on the year, right? Get or else books, okay? And we do the same with the limit. If the limit is specified, we take the specified amount of books, and now we have to provide a response. Well, in that case, we are always successful, so we return a write, books too. So if you look at the signature that's actually required here, we have specified that from the request we read two optional values, right, the year and the limit, and we return either an error, so that's the error output on the left of an either, as is conventional in Scala, or we return success, which is a list of books on the right of an either, right? So here we return, why is everything so red? That's not good. Yeah, the bracket's in the wrong place. Okay. And I'm comparing years and like that. Yeah. Okay. This should work. And so yeah, so we are returning the result in a very similar way. We can implement an endpoint to get a specific book. Okay, so that was one interpreter, but we can also interpret the routes in another way, right? We can import another interpreter, for example, the OpenAPI interpreter. So what we can do now is we can take a list of our endpoints, getBooks endpoint and getBook endpoint, right? And a single one. And of course, I forgot this as well. So this interpreter adds another extension method, right? So here we had an interpreter which added an extension method to interpret an endpoint as an HTTP4S route. Here we have an interpreter which allows us to convert an endpoint or list of endpoints to an OpenAPI object. So we need to provide the title and the version. And what we get is an OpenAPI object. So this OpenAPI object is, if you take the OpenAPI specification and you convert it to case classes, that's what you get, right? There's a long list of case classes, which is a direct translation of the OpenAPI specification, right? So what we do here is we convert this description of our endpoint to the OpenAPI classes. The last thing we need to do is we need to serialize the OpenAPI as YAML. So we import tapir OpenAPI Cersei YAML. Cersei can also serialize to YAML, and we call docs.toYAML, and we have the YAML over here, right? Okay, so now we can actually try running that, and we'll see if it works. It should actually compile. And what we should be able to do is we should be able to look at the documentation and invoke these two endpoints. Okay, success. Almost. Yeah. Okay, so we have our documentation generated. We can try invoking this endpoint, and it actually gets a list of books, right? So the Sorrows of Young Werther, a very nice book. We can filter by the year. What's an example year, for example, here? 1774. Let's see if we get only one book. 1774, execute, and we get a single book. Okay, so this worked. So that's how tapir works. And what we have seen here is a more general technique in play, which is to separate the problem description from its interpretation, right? So what we did is we described the endpoint as an immutable data structure, and then we provided a couple of interpreters that turn this data structure into some usable thing, like a server, or we could also interpret it as a client, or as documentation. So we added, like, comparing to like HTTP4S or HTTP, we added a level of indirection, right? In HTTP and HTTP4S, you describe the endpoint together with the server logic. Here we have these things separately, right? We have the description that is separate from the additional data that might be needed for a specific interpreter. And this technique is widely used in functional programming. So, for example, let's take a look at other libraries. So you might or might not know Dubi. Dubi is a library for working with SQL databases, and it uses exactly the same approach. So here we have, in Dubi, the central construct is connection IO, right? A connection IO is a data structure which describes operations on a database, right? And Dubi provides a nice API on top of that to create instances of the connection IO values, which describe. So here, for example, we have a description of an insert query, which is an update, right? So it won't return any results. Here we have a description of a select query, which returns a single number, and so on and so on. There's also an API to actually compose these descriptions, these single statement descriptions, into descriptions of what should happen in an entire transaction. But at the end of the day, if we run this code over here, only this code, if we run this code, nothing will happen really, right? There will be some memory allocated, the data structures will be created, but nothing will happen in the database, right? Because it's only a description. It's an immutable data structure describing what should happen when we talk to the database. Only when we use an interpreter, and in Dubi's case, the interpreter is a transactor. So a transactor holds a connection pool to the database, and it knows how to translate this description into specific database calls, right? So that's our interpreter over here, and that's where we run the interpretation when we call transact on a description of operations. So that's Dubi. A very similar thing happens in Zio, or in Monix, or in Cat's Effect. They more or less work the same. So in these libraries, you create an immutable data structure, a description of how an asynchronous or concurrent program should work, right? So we have constructors to encapsulate some effectful functions. We have constructors to loop. We have constructors to run something in the background, to fork, join, and so on. So we have all the tooling to describe asynchronous and concurrent programs. But still, a Zio program or a Monix program, it's just a data structure, right? Nothing will happen if we just create the data structure. We need to provide an interpreter, and in Zio's case, the interpreter is called the default runtime. And once we interpret it, things will actually happen. And these two are actually examples of a more general, even more general technique in Scala, which was once very fashionable, the free monads. And the free monads work basically on the same idea, right? We have a base, so a free monad is a way to describe a sequential program using Scala, using a data structure which uses some base instruction sets, right? So in a free monad, you have to provide the base instruction set, which are reified as case classes, and the free monad gives you sequencing of two programs, so flat map, and the ability to return a value, so pure, for free, right? So you can look at the CATS tutorial. They show how to describe a program which operates on a key value store. Again, it's just a data structure. If we want to actually run the program, we need to provide an interpreter, a compiler for our program, right? So we need to provide an interpretation for each of the basic instructions. So we need to specify what kind of side effects they do, right? That's only when things actually happen. And in fact, And in fact, both Zio and Dubi are instantiations of the free monad using a very specific instruction set, right? So in the case of Zio or Monix, the instructions are tailored for concurrent asynchronous programming. In case of Dubi, the instruction sets are tailored for working with the database. In case of tapir, well, that's not a monad, so the free monad doesn't apply here. So tapir is one thing in Scala that's not a monad. Okay, so let's talk about a couple of design choices in tapir. And more importantly, what are the trade-offs of the library that the library makes? So before doing that, let's look at some goals of the API. So when we started writing tapir, what were the main goals of the library? So first of all, of course, we are in Scala. So we want to be type safe. We want the compiler to do the boring work, right? And we want to do the interesting work. That's what the compiler is for there, right? So we want our library to be type safe. So that's like the guiding principle. However, we also want to be programmer friendly, and that also means programmer friendly types, right? We want types that you are able to write down by hand, that you are not only, probably the types can be inferred by the IDE, but even if they are inferred by the IDE, you don't want to be scared by them, right? You want to be able to understand what's in the type. So not only the code has to be readable, the types need to be readable as well. Well, the types are part of the code, you could argue, right? And another thing is an API should be explorable. So the standard way of getting to know a new library, right? When you start working with a library, you probably type in some name of a starting class or a starting object, and you look what control space gives you, right? So you look at the auto-completion list, and you can see what you can actually do with it, probably before reading any documentation. So this should work fine with the library. Auto-completion is one of the main tools when discovering what we can do. Same for go to definition, right? We want to be able to easily jump to the definition of how things actually work. Well, when understanding how a library works, go to definition and find the usages are the most useful tools. Try doing that on annotations. If you try to go to the definition of an annotation and then finding its usages to see how does it really happen that an get an annotation actually causes one endpoint to be exposed as a get method, well, it's not possible to find that. Okay, so diving a bit deeper, type safety. So tapir actually has one place where we do type level computations, which are quite crucial for the library, and that's when we define the inputs and outputs. So let's look at the first type parameter of the endpoint over here. And so the first type parameter specifies what kind of values are extracted from the request or what kind of values are mapped to the request, right? So if we take the starting endpoint, which is an empty endpoint, and we add a single input parameter, right, which is an int, well, we get an endpoint which takes a single int, right? And that's an immutable value, so we can just take it and specialize it further. So now we have this endpoint with a single input parameter, and we add a second type parameter. We add a second input parameter, which is a string body, so we will get a string from that, right? So now the type of this endpoint has to be the type parameter of that endpoint has to be int and string, a tuple, right? And that's where we actually need to do some type level computation, which is concatenating what was here before with the new type over here, right? Well, that's of course like pretty standard type level computation in Scala, but it's not something you could do in other languages. And we can do it incrementally further, right? So here we add a UUID parameter, and we get a triplet from a tuple and so on. So that's of course done using implicits, but they're not scary if you want to look at them. But that's like a crucial component of tapir and of its type safety mechanism. thanks to these type parameters over here, when we define the server logic, for example, we can do it in a type-safe way, right? So even the ID, it's not only the compiler, but even the ID can tell you that the type of the function that you have to provide to turn this endpoint into a server, it needs to take one parameter which is a triplet of an int-string and UID, like so the parameters we had defined as an input, and return, well here we don't return anything interesting, so we return just units. But if we specify an output parameter, you would see different things in the either. And that also that also brings us to the reusability point when we talk about immutable case classes. So that's also something that's not really possible easily with annotations. So when you define endpoints, you probably start seeing patterns in how these endpoints are defined, right? So there will be probably some repetition. Like over here, for example, you can see that, well, these endpoints really have quite a lot in common, right? They're both get endpoints, they both have books as the first input parameter and so on. So what we can do, remember, these are just immutable data structures, values, right? So we can create, for example, a base books endpoint, and we can say that the base books endpoint is an endpoint.get in books. So we extract the common parts into a value, right? And now we can use that value instead of these things over here, right? And the type is the same, of course. Another thing that repeats itself here is the description of the error output. So in this case, the error output consists of a status code and a message, right? And it's repeated 2 times over here. So what we can do is we take the description of the error and we can actually extract it as a value. So books error output will be this, and we will use it over here and over here, right? Furthermore, like there's one more repetition, the error out is repeated, so we can extract it and use it over here and over here, right? And things get more concise. And note that we are using very standard tools, which is extracting the code that's repeated into a value, right? Now, yeah, we can add types here so that everything is nice and readable. We can see that the description of an output is of type endpoint output, so nothing very surprising, right? And we map those. So here we create a tuple and we map it to a case class. We can as well, instead of val, we can have a method which maybe takes some parameters and returns the error output parameterized depending on in what context it's used. So we get all these standard abstraction tools because these are values, right? And it's the same if you use Dubi, if you use Xi, if you use Monix, if you use Tapir. It's the same techniques. We just work with case classes, we work with data structures which we can manipulate, abstract, and so on. Okay. So changing the subject a bit, an important design decision in the case of our library was deciding what should be the shape of the function that we want to describe, right? As I said, it might be tempting to describe any function, just any function which takes an input to an output, right? But that might be it might be possible, but it would probably not be that very useful and might be too general. So the first thing that we restricted ourselves to is describing functions which end either in an error or in success, just because it's so common in HTTP that you actually get errors or successes, and that they are usually have different response types, right? So we restrict we restrict the shapes of the functions that can be described by Tapir to this shape return in an either, right? But in the end, for the HTTP use case, we get a more user-friendly API, right? And that's if you look at the endpoint, that's what actually the server logic function, that's the shape of it. However, that's not the end, right? What's the shape of the input then, right? Let's now focus on this input parameter over here. Well, of course, it can be an input can be a single value, or it can be a tuple, right? So it can be a product. We can take 2 inputs and say that we want to take we want to read both of these inputs. So we can take products. Once we have products, you can ask, what about coproducts? Of course. So what about coproducts, right? Do we want to be able to describe inputs which can be either one or another one, right? Well, again, seems tempting, like we like symmetry, right? So why not coproducts? Well, they complicate things a lot. So when you go into coproducts, into eithers, you need some kind of discriminator. So you need to be able to tell when to use which alternative, right? So it would be probably possible, but we didn't really find any practical use cases, so you cannot do it, at least for now. In Tapir, and the API is much simpler. You can still, there is a fallback, you can still represent eithers as a tuple of options and do additional server-side validation. So you can represent those type of endpoints if you absolutely need to, but kind of more by hand. And a similar thing with outputs, right? Outputs, well, they can be products as well, but there already is a top-level coproduct in the output, which is the either, right? And here the discriminator, we have a good discriminator for that. We have the status code, right? If the status code is 200, we have success to the right case, and if it's 400 or 500, we have the left case, right? So here we have a good discriminator, and so we have the top-level coproduct. You can also specify lower-level coproducts basing on the custom status code. So you can say that, for example, if the status code is not found, you should respond with this JSON body. Yeah, thanks. If the status code is unauthorized, you should respond with this body, and so on and so on. But that's the only type of coproducts that are supported as well, right? So again, we restrict the possibilities just to make the API nicer. And while we are at restricting, going back to type safety, well, you also have to consider which properties do you really want to verify at compile time, right? Do you want to verify everything at compile time? Well, probably not. So what we verify at compile time, I think, is the most important parts, which is the types of the inputs and outputs. These are the most usable parts, right? So when you have a query that's an integer and a string body, you will actually get the server logic that is parameterized by the right values. Oh, here we output the string body, not input. So we do verify at compile time that the type of the body is actually correct over here, right? So that it matches the description of the endpoint. What we don't verify, for example, is that you have specified a body input twice, right? So here there's an endpoint description where we specify that we read the body as a string and as an array of bytes. So that's probably wrong. That's probably not what you meant. However, this is going to be a runtime error, not a compile time error, right? To track this information, so to track if an endpoint has a body or not, that would complicate the type a lot, right? So the endpoint type would be really much more complex and much more complicated. The benefit from getting this additional verification would be, I think, much smaller from the actual cost on the complexity of the endpoint type, right? So you have to pick, like, what do you want to verify at compile time. It's not everything in our case. It's just the most important parts. Okay, so two last things. One important thing is a very technical thing in Scala, but I think it's nice to know. If you look at the function over here, so if you have an endpoint which has two input parameters, so a tuple, and you specify the server logic over here, so what you need to provide is a function taking these input parameters and returning some result. However, initially you might think that this is a function taking two parameters, and that's not the case. It's function taking one parameter, which is a tuple, which is different, right? You can have a two-argument function or a one-argument function taking a tuple. So that's carrying, uncarrying, and so on. So again, technically, it would be possible to do some type level computation and accept a two-argument function from the user, right? That may be a bit more natural. However, to do that translation from a tuple function to a argument to a two-argument function, well, that would make the types much more complex. It wouldn't be possible for the IDE, for example, to figure out the types that are needed here. So again, that's a trade-off that you have to make. And instead of writing the function like this, well, you have to deconstruct the first parameter with a case like this. Okay? And the last thing I wanted to mention is that however nice and your API is, you actually probably want to have some kind of backdoor, right? You won't foresee all use cases and all kinds of ways that people will actually try to use your library. So it's good to have a way like to do anything, right? And there is a way to do anything in Tapir, right? We can describe an endpoint, and that's this n endpoint. So we can describe an endpoint which takes all headers, all query parameters, all path components, reads the body as a stream, and returns any headers, any body, and so on and so on, right? So that is still possible in Tapir. You can return anything. So in case your use case is not covered by the high-level API, you can use that. So it's good to have a backdoor. So yeah. So summing up. Yeah, we've seen a demo of Tapir. We've seen the general technique of separating description from interpretation, how you use immutable data structures to describe the problem, and various interpreters to then provide specific use cases. We have seen that we have the API on top of these case classes to provide nice syntax to create the data structures. We have seen how we restrict the flexibility of our API to match the domain better. And finally, a way to provide a backdoor. So if you would like to follow the code from the presentation, it's available on GitHub as well as the library. And if you would have any questions, I'll be here, of course, because I think I'm out of time. And thank you very much.
Спасибо за хороший доклад, было очень интересно.
Спасибо.
Да, мы хотим вам подарить вот это.
Okay. Thank you very much.
И футболку. Собственно, на вопросы времени не осталось, так что продолжим в дискуссионной зоне. А сейчас будет готовиться следующий доклад. Всем спасибо.